The next thing we're going to talk about for confidence intervals is for population standard deviation and also population variance, since the two of those go hand in hand. So we know that the sample variance, which is S squared, is going to be the best point estimate for the population variance, which is sigma squared. So remember, sample variance, you would go ahead and you would take samples of whatever size it may be. You go ahead and find the variance for that specific sample, and then you repeat that process however many times, and then you get a whole list of different variances. Then you would take the mean of that, and that gives you your sample variance. So that one we know is an unbiased estimator. When we're talking about standard deviation, we're still going to actually just use S for a point estimate for sigma. We know that this sample standard deviation is going to be a little bit biased, but it's so negligible that it doesn't matter. So again, these two go hand in hand because once you have the sample variance, you just take a square root to get the sample standard deviation. And the same way, if you know the population variance, the square root of that is going to be the actual population standard deviation. Now, the thing is, when you go through and you create these sample variances and sample standard deviations, what ends up happening is you don't get a normal distribution. Remember, you get something that's a little bit skewed instead. So when we go ahead and we find the sample means, that we figured out had a normal distribution, which is why we ended up using the t-distribution, because it gave us some more wiggle room. Here instead, when you find all these different sample variances, the distribution of that is skewed, and we're going to be using something called the chi-squared distribution. So it gives us that shape of the distribution of sample variances. So we're going to construct confidence intervals in a very similar manner for both the standard deviation and the variance, but it's going to be using the chi-squared distribution. So what that is, chi is just a Greek letter. So chi looks like this. It's kind of a fancy X. So one of them is swiggled a little, or can't think of the right word, but squiggled. And then it's chi squared, so it gets a square on it. Don't mistake this for actually squaring something. This is a notation to indicate it is chi squared. So the way we find this, just like we have for t-distributions and like we have to convert something to standard normal, the way you find the chi-squared is going to be you take the sample size minus 1, you times it by the sample variance, and then you divide by the true variance. So again, this is the thing that we're going to try to be estimating, so there is going to be error associated to it. So again, when you go through the process of finding all these different sample variances, if you were to plot that histogram, it's actually going to look something like this. So this is our chi-squared distribution. So what happens is you're going to notice that the thing that's right in the middle, or that tallest point, is now no longer the center. So this is not symmetric anymore. But the other nice thing, or the one nice thing about it, is you're going to see it always starts at 0. So there's some nice properties that happen with this. So ultimately, what we're going to be doing is we're still trying to find the same thing. If we want a 95% confidence interval, I need to figure out what is this cutoff value and what is this cutoff value, so that the area in between is 95%, 99%, whatever it may be. So these have different names. This one here is called chi-squared, and then it's the right cutoff. So here it leaves you with a right tail. And then the one over here is going to be chi-squared left tail. So we use an L to indicate that. And because of the non-symmetry, these two tails end up actually having the same area, but they're going to occur at different values. Okay. So to give you kind of just some background on this chi-squared, the right-tailed critical value is denoted by chi-squared r. So again, that has a tail to the right of it. And then the left-tailed critical value is denoted by chi-squared to the left. Okay. You're also still going to have degrees of freedom for this. So the degrees of freedom is still the same. It's one less than the sample size. So the degrees of freedom is the sample size minus 1. And again, those degrees of freedom are going to dictate exactly what that chi-squared graph looks like. So you can see over here, when your degrees of freedom is 10, you have something that's skewed pretty far so that the bulk of the data is sitting to the left. But then when you increase and have more degrees of freedom, that graph starts moving to the right. If you increase the degrees of freedom again, you'd probably see it would look something like this. So what ends up actually happening is as the degrees of freedom increases, the chi-squared distribution approaches a normal distribution. Which is just like the t-distribution. The more data you have, essentially, the closer and closer it's going to look like something normal. And then as the last bit, the chi-squared is skewed to the right, meaning you have a large tail to the right side. And it's non-symmetric. And this is important for us. So I'm going to go ahead and highlight that because this is a big deal. We no longer have symmetry like we did with normal distributions or with t-distributions. And then the last feature is the values of chi-squared are always going to be 0 or positive. You will never get a negative output. Okay. So leaning into this non-symmetry, that is going to mess up our process a little bit. I'm still finding error in a similar manner. I want whatever percentage of data to fall between two critical numbers, but finding the critical numbers is a little bit different. I no longer have the same margin of error on either side. So because the chi-squared is not symmetric, the confidence intervals can no longer be expressed as the following. You can't say your actual population variance is smaller than the sample variance plus some margin of error, or the sample variance minus some margin of error. This no longer is going to make sense. Because we don't have symmetry, that point in the middle is no longer exactly in the middle, and these two values are not going to be one positive, one negative. So instead, what's going to have to happen is we're going to do separate calculations for the upper and lower bounds on those confidence intervals. And there's still a table to figure out what those actual critical values are. So to kind of just go to that, and we'll do an example with it. You're going to see here's our chi-squared distribution. It's kind of split right down the middle here. So this gives you the area to the right of the critical value. So in this case, this would be 99.5% of the data is to the right, 99% of data is to the right, 97.5%, 95%, and 90% is to the right of that critical value. And likewise here, these are the areas to the right. And then we have those degrees of freedom off to the side. And in this case, we're only going to go up to 100 degrees of freedom. So what happens here is you have that distribution that has non-symmetry. So if you want 90% confidence interval, That means 90% of your data is going to fall in between, and you still want symmetry in terms of area on either side. So 5% would have to go here and 5% would have to go here to give you that total of 100% of data. So in this case, to find this critical value over here, you need 5% of data to the right, so you'd be looking in this column. To figure out your critical value on the left-hand side, instead, you need 95% of data to be the right of this line, so you would look here, okay? So let's try an example with this. We're gonna find a simple random, or we're told a simple random sample of 22 pulse rates is obtained. We wanna find the chi-squared distribution to the left and right, those critical values corresponding to a confidence level of 95%. So I do need my degrees of freedom to be able to use my chart correctly. So my sample size is 22 pulse rates, which means my degrees of freedom is 1 less. So we take our sample size, subtract 1 to give us 21. I like to draw a picture for these to be able to see what my left and right cutoff values are. So I'm gonna go ahead and draw the bottom. This is my starting value of 0. Go a little bit past it. And then our chi-squared distribution starts at that and then goes to the right. I want a 95% confidence interval. So that means I need some value here, which is the left. And then I need some value here, which is the right. And I want 95% of data to fall in between the two of these. Which means on these outskirts here, that's 5% of data. So what's going to be to the right of this value is 5% divided by 2, which means 2.5% of data falls to the right of this critical value. And really, same thing ends up being here. 2.5% of data values fall here. So I always like starting with this one because it's a little bit easier to calculate. But the area to the right of this critical value is going to be 2.5%, which as a decimal is 0.025. So if I go to my chart, I have 21 degrees of freedom, which is going to be this row right here. And my area to the right should be 2.5%. So if I go down to 21 degrees of freedom, that tells me this critical value is 35.479. So that critical value is 35.479. Now to figure out this number, I also need the area to the right of that. Before I can use my chart. So the area to the right of our left critical value is, well, this has to be 2.5%. The whole data has to add up to 100. So really from 1, you're going to subtract 2.5%. So really 97.5% of data should be to the right, which as a decimal is 0.975. So I can use my chart to figure out what this left critical value is. So going back down, we have 97.5% of data to the right, and I need to go to 21 degrees of freedom. So this critical value is 10.283. So my other critical value is 10.283. Okay. So finding these critical values are kind of the crux of the whole problem. As soon as you have them, it's a matter of just plugging it in to figuring out the different bounds. So we'll go through how to construct this confidence interval, and then we'll do an example. But we do have some requirements to be able to do this. The very first is that the sample you're working with needs to be a simple random sample. The second, if you remember back to the other, you either needed to have normal distributed data values, or you needed your sample size to be big enough. Here we have a little bit stricter. Your starting population must have normally distributed values. So the sample size does not make a difference. The population must have normally distributed values. So as long as these two things are satisfied, we can go ahead and find the confidence intervals for both our variance and our standard deviation. As long as you know one though, remember to get the other, you just go ahead and you take a square root. So the confidence interval for our variance is going to depend upon those left and right critical values. And that upper bound is going to be n minus 1 times our sample variance. And then here you're going to divide by the leftmost critical value. Seems kind of counterintuitive because it's on the right, but you're going to use the left value. Realistically, when we go through an example, you'll see exactly why, because this lower bound is the same thing, but you just use the other critical value. And in these cases, basically, once you calculate each of these, you're going to see dividing by this results in a smaller value, while dividing by the leftmost critical value results in something bigger. So immediately you'll be able to set up that interval because you have a smaller and larger value. Then when you want to go for the interval estimate for just our standard deviation, all you're going to do is take a square root. So again, once you have 1, to get rid of the square, you take a square root, which means you have to take a square root of each of these, okay? So let's go through and let's try an example, finding all of these pieces, finding our critical values, and getting that confidence interval. So we're told a simple random sample from a population with a normal distribution of 101 body temperatures has a mean of 99.2 degrees Fahrenheit and a sample standard deviation of 0.65 degrees Fahrenheit. We want to construct a 99% confidence interval estimate of the standard deviation of body temperatures. So again, I got to make sure those requirements are set. I'm just not going to write them down, but we have a simple random sample and that population has a normal distribution. So I'm all good. So I need to first figure out my degrees of freedom because that's going to tell me which row I have to look in my chi-square chart. There are 101 data samples, so my degrees of freedom is 1 less. So we have 100 degrees of freedom. I need to figure out those critical values, and then I can go ahead and find my upper and lower bounds. So again, I like to draw a picture for this. So here is my chi-square distribution. Here is my start at 0, and then I go up and I go down. So I want a confidence interval of 99%. That tells me I have some value here and some value here. And that means 99% of data is going to be in between. This is going to be my right critical value. This is going to be my left critical value. If 99% falls in between, that leaves 1% for these outside. So that means this area is going to be half of that. So this is 0.5%. And then likewise, this is the same. This is also going to be 0.5%. So to find these critical values, we use our chart, but I know the area to the right of this critical value is going to be 0.5%. So as a decimal, that's 0.005. Because to get that, you just move the decimal 2 places and then fill in those gaps. So this tells us our rightmost critical value. I have 100 degrees of freedom and I need 0.005 to the right. So going to my chi-square distribution, here is my 100 degrees of freedom, and it does fill in the blanks here. The area to the right is 0.005. So this right critical value is going to be 140.169. So at least it's a little bit nice because I get to use that bottom chart. So this is 140.169. Now I need to figure out this critical value. So the area to the right is going to be 1 minus this 0.005. So the area to the right of the leftmost critical value is 1 minus 0.005. So that means 99.5% of data is to the right of this value. And I shouldn't say these are equal. I should say the area to the right of this is this amount. And so going into my chart again, we're in that bottom row with 100 degrees of freedom. The area to the right is 99.5%. So this particular critical value is 67.328. So our value of the leftmost critical value is 67.328. So what I'm going to do, because we're working with the estimate for standard deviation, we're going to need to find these two particular values. So from here, I need to find what is the square root of n minus 1 times that sample standard deviation squared over my right critical value. And I'm really going to do the same thing with my left value. So here, n minus 1 is the degrees of freedom minus 1. That's 101 minus 1. They tell us our sample standard deviation is going to be 0.65. So this will be 0.65 squared. And then our rightmost critical value is 140.169. You do not square it. Again, that square on that notation is just standing for chi-squared. So if you plug this into your calculator, you'll see this is about 0.55. So that gives us one of our bounds, and you're going to see it, and it's smaller the value, so it's going to be the left bound. If I do the same thing now with my other critical value, you're still going to do 101 minus 1, 0.65 squared, but now in the denominator, it's going to be 67.328. So if you plug this into your calculator, you should see this is about 0.79. So when you divide by the bigger value, which is of course going to be the right value, you end up with something smaller. When you divide by a smaller value, which is the leftmost value, you get a quantity that's bigger, which is why these two are your bounds. This is the smaller, so it's the one that goes first. So there is 99% confidence that our actual standard deviation is bigger than 0.55 degrees Fahrenheit, but less than 0.79 degrees Fahrenheit. And if you wanted the sample variance or estimating the variance, all you would do again is the same thing. You just wouldn't have these square roots here, or you really just square the number that you get. Okay? So again, just a slightly different process, but still the same idea. The one thing that is going to be much more complicated is finding that sample size you need to appropriately estimate your standard deviation. It is way more complex than finding the sample size needed for proportion or mean. So realistically, we're just going to have a table that's already done all these calculations for you. So we have 99% confidence and 99% confidence. And what this is basically your error that you want. So to be 95% confidence that your standard deviation is within 1% of your actual standard deviation, you would need a sample of 19,205. If you wanted to be 99% confidence that your sample standard deviation is within 1% of the true standard deviation, you would need a sample size of 33,218, okay? So this is a matter of just reading the table. So we're just going to do a single example for this. Assume a simple random sample is obtained from a normally distributed population of IQ scores. We want to find the minimum sample size needed to be 99% confidence that our sample standard deviation is within 50% of the true. So if I'm working with 99% confidence, that means I'm going to use this table, and I want to be within 50% of my actual standard deviation. So the sample size I would need would be 14. So using our table, the sample size we would need is 14. And that's definitely feasible. Having a sample size of 14, not too bad. But having a sample size of 33,218, that would be very difficult to do.